The three types of inhibition we will be learning about today are competitive inhibition, uncompetitive inhibition, and mixed. You may hear mixed referred to as non-competitive, but I think it's confusing to have competitive, uncompetitive, and non-competitive. So competitive, uncompetitive, mixed it is. Let's start with competitive inhibition. This is kind of the simplest to think about, so it's a great place for us to start. A competitive inhibitor binds to the active site and directly competes with substrate. So let's take a look at that in the equations we have here, the reaction schemes on the slide. So we have our enzyme. The enzyme can either bind substrate or it could bind to inhibitor. It cannot bind both. You also see that when enzyme binds substrate, a reaction happens. We form product. But when enzyme binds the inhibitor, no reaction generally is going to take place because the inhibitor is not the substrate. How can we identify a competitive inhibitor? By looking at its Lineweaver-Burk plot. So let's rearrange our mind here, folks. Let's focus in on this Lineweaver-Burk plot. What are we seeing? Right, the double reciprocal plot. So on the x-axis, we have 1 over substrate concentration, and the y-axis 1 over initial velocity. Remember, we use these types of plots because it linearizes the data and lines are super easy to work with. Let's also keep in mind, folks, that the y-intercept is 1 over V max, and the x-intercept is -1 over Km. I apologize that my head is right in front of what I just drew. I need to remember not to draw in this corner. It says y-intercept equals 1 over V max, x-intercept equals -1 over Km. We use this plot because it clearly shows us the Km, the V max. A competitive inhibitor plot is easy to identify because all of the lines intersect at the y-intercept. So you see that a competitive inhibitor has no effect on the Vmax of an enzyme as we go from line 1 that has no inhibitor to line 2 that has a little bit of inhibitor and line 3 that has a little bit more inhibitor. But as we add inhibitor, you can see that the Km is moving closer and closer to the axis. So the Km appears larger, right? If -1 over Km is getting smaller, Km is getting larger. Why does this make sense? Let's draw ourselves how a competitive inhibitor works so that we can understand this. So here's an enzyme, enzyme E. Here's substrate, and here's inhibitor. A competitive inhibitor binds the enzyme's active site. So you notice how I've kind of drawn the inhibitor and the substrate to look about the same. Keeping in mind, I am no artist. So what can happen, folks, is this enzyme is either going to bind substrate or it is going to bind inhibitor. When it is bound to substrate, we have a reaction and we can produce product. I'm sorry, this arrow is pointing to product. But when the enzyme is bound to inhibitor, there is no reaction that happens. So why does Vmax not change? Vmax does not change because when enzyme binds the substrate, the reaction can proceed as it always has. It proceeds uninterrupted. The inhibitor does not interact with the enzyme at all if the substrate is bound. So Vmax can't change because when enzyme is bound to substrate, the reaction just goes. Km, on the other hand, appears to increase because what's happening is the inhibitor is literally blocking the enzyme from binding its substrate. So a lot of the time it looks like the enzyme can't bind the substrate. We know that enzymes with larger KMs bind substrate more poorly, right? Well, of course, if the enzyme is now sometimes binding inhibitor, it looks like it's binding substrate more poorly. So the Km increases because the inhibitor competes for binding. So enzyme binds substrate less often, or we can think about it as less well. That is the first type of inhibitor, competitive inhibitor. Before we move on to the next type of inhibition, I do want to make a couple quick points about competitive inhibitors. One special type of competitive inhibition is called product inhibition, and this will become important in future lectures, especially once we start talking about metabolism. So what can happen, folks, is if this reaction keeps going and going and going, eventually we will have a lot of product being made. And so what can happen is the enzyme then has the capacity to either bind substrate or to bind its product, right? We know that the enzyme can bind substrate because it's its substrate. But we also know that the enzyme can bind the product because the enzyme makes the product. However, if enzyme is stuck bound to product, no further reaction is going to happen of the substrate because the product is outcompeting the substrate. So I wanted to mention this to everyone because product inhibition will be discussed in this class. And the last note I want to leave you with, folks, is that lots of drugs use competitive inhibition as their mechanism. For example, many HIV drugs use this mechanism. For example, various nucleoside analogs will compete with nucleotides to prevent the HIV from reproducing in your cells. Additionally, we have some cool transition state peptide analogs that will not be inhibiting production of the nucleic acid, but would rather be inhibiting the protease of the HIV. So I thought those were interesting to briefly mention to everyone, as competitive inhibitors are super, super common. Up next on competitive inhibition.